Hi all, welcome to the session. Myself, Dr. Rakesh Chandan SD, Assistant Professor, Department of Physics, Sanadana Dharma College, Alappuzha. In this lecture series, I like to discuss the topic Dynamics of Rigid Bodies, which covers the entire syllabus of Physics Complementary, Semester 1 Physics Complementary for Mathematics and Chemistry under University of Kerala. So after watching the video, if you have any queries, please feel free to contact. My mail ID and phone number are here for your reference. So let's move to the topic. So these are the topics which I like to include in this session. So first I will give you a brief introduction on specific themes which are there in our title heading. Then we will learn rigid body dynamics. After that, we will introduce the similarity or difference between mass and moment of inertia, which is very important in this session. After that, we will define moment of inertia using different terms, and we will discuss two theorems of moment of inertia, which will be very useful to find out the moment of inertia of different bodies of various shapes. So these are the topics, and first of all, I like to describe two terms which are there in the title heading. You know, the title heading is Dynamics of Rigid Bodies. So we have two terms, dynamics and then rigid body. At the very outset, we will discuss what is this dynamics. As you all know, dynamics is a branch of mechanics which is mainly concerned with the study of forces and their effects on motion. So mechanics, it is broadly classified into two, dynamics or kinematics and statics. And static is concerned with the forces or study of forces and their effects on the bodies which are at rest or at equilibrium condition. But dynamics is mainly concerned with motion. So in this portion or in our syllabus, we are dealing with this dynamics of rigid bodies. So dynamics, it helps us to predict the motion of objects or objects under various forces such as gravity. It helps to predict the motion of planets in the solar system, or it helps to predict what is the distance a car will cover at a particular time. So it helps to understand the everyday things that are of interest to many of us, which includes physics of sports and physics in amusement parks, etc. You know, in sports, especially in cricket or basketball, hockey, the dynamical equation or physical laws are playing a major role there, or in the amusement parks also, you know, in many rides, they are just working based on the principle of physical laws. So in this way, dynamics plays a major role in our everyday life. So in short, we can say Newton's equation of motion, they are the backbones of many theories which are derived in dynamic branch. But do you believe Sir Isaac Newton was a pioneer to introduce the foundation of dynamics? No. So it's Galileo. Galileo was the first one who laid foundation of dynamics at the end of 16th century. He actually derived the equations of rolling bodies on an inclined plane, and he who first stated forces are the real cause for the change of velocities in bodies, which is very important during that time. And before Galileo, you know, Copernicus, he also worked in the field of equations which governs the motion of planets, and he who first stated sun is the center of the universe. So in this way, many physicists or scientists have worked in the field of dynamics, but it got wide acceptance when Newton published his Newton's equation of motion in Principia Mathematica in 1687. So in short, we can say nothing that moves can be analyzed without the use of dynamic concepts. So this is the importance of dynamics in our everyday life. So this is the importance why we need to learn dynamic equations in our physics syllabus. So the study of dynamics falls under two categories. It may include the linear motion and rotational motion. Dynamics of linear motion and rotational dynamics. In this syllabus, we focus only the rotational motion of rigid bodies. So next we need to learn what is a rigid body. So you know, it is a solid body in which particles are compactly arranged. Particles are compactly arranged so that the interparticle distance is small and fixed. We can say this one is a rigid body. So here the particles are compactly arranged, or their relative position remains unchanged because of external force or torque. So in rigid body, in motion, they won't bend or oscillate or vibrate. They keep their configuration or shape intact during the motion. So this is very important. So the particle distance remains fixed when a rigid body undergoes a motion, whether it is translatory or rotatory motion. In the figure you can see a rigid body. So it is very solid. The particles are very compactly arranged so that it has the freedom to rotate, it has the freedom to move in a straight line. So this is the main thing about rigid body. So we are considering the motion of rigid bodies, especially the rotational motion in this syllabus. So this statement, it is very important. A rigid body preserves its shape or configuration intact during the motion. In the figure you can see two types of motion, translatory motion and rotational motion. The first figure you can see a car which is running along a straight road, and the second figure you can see a cycle wheel which is free to rotate about a fixed axis. In the first figure you can, I am just considering 3 points A, B and C. So in the first figure, if the car moves along the straight road, these 3 points also moves with the same velocity, parallel to one another and along the straight line. If this is the case, we can say rigid body is executing translatory motion. So in the translatory motion, rigid body, in the particles of the rigid body need to travel with a velocity, with same velocity, parallel to one another along the straight line. Then we can say the rigid body is executing translatory motion. Here you can see all points have exact same velocities and move along identical or parallel paths. But in the case of rotational motion, the particles are free to rotate in a circular path about a fixed axis. Here you can see the particles are free to rotate about a fixed axis and the path is circular. Here you can see there is a velocity. In the case of translatory motion we have velocity, linear velocity, but in the case of rotational motion, you know, we have angular velocity. So I told you, if a rigid body is executing rotational motion, the particles are moving along circular path about a fixed axis, and that axis which passes through all the centers of such circles. You can see this is a rigid body. This is a rigid body, and you can see different particles. I am just considering 3 particles, and these 3 particles are following circular paths of different radii. You please note, they are what? They are just executing circular path of different radius, because the particles which are very near to the axis is executing or following small circular paths, and the particles which are at some distance from the fixed axis is following larger circular path. But you can see an axis which passes through all the centers of this circular path, and this axis is called axis of rotation. Based on the position of the axis of rotation, we can further divide the rotational motion into spin motion and revolution. If the axis of rotation of the body is within the body, then we can call that motion as spin motion. You can see this one, the spinning motion of a top, spinning top. Also, you can see spinning of cricket ball. So these motions comes under spin motion because the axis falls within the body or inside the rigid body. But if you consider a situation in which the axis of rotation stays outside, then we will call that one as revolution. Here you can see a rigid body. So this is a shape. We are just giving some irregular shape for a rigid body. So in this rigid body, you can see two particles also. It consists of infinite number of particles, but for the discussion, I am just taking two particles. But here you can see the body is executing circular motion about an axis which lies outside the body. So if the axis of rotation lies outside the body, we will call that motion as revolution. You know rotation of the earth and revolution of the earth around the sun. The revolution in the revolutionary motion, the earth is revolving around the sun. In the rotational motion, the earth is rotate about its own axis. So these are the two things or two categories which comes under rotational motion. One is spin motion and the other one is revolutionary motion. Hope you understood. And also we need to discuss the plane of rotation. So as I discussed earlier, when a body executes rotational motion, the particles are following circular path. They are executing circular path about a plane which is perpendicular to the axis of rotation. If the particle is executing this manner, circular motion, you can see the particles are executing circular motion along a plane which is perpendicular to the axis of rotation. Then we will call that one as the plane of rotation. So in the case of revolution of planets, we have the plane of orbits. So this is the thing we need to include in the first part, dynamics, then rigid body. So we discussed dynamics and we discussed rigid bodies and what are the different types of motion, and we need to concentrate more on rotational motion of rigid bodies. Okay. The next topic, which is very important, mass and moment of inertia. You can see, as per Newton's first law of motion, a body will continue in its state of rest or of uniform motion. Our body is very much like to be in the state of rest or of uniform motion, and this property is called inertia. Obviously, you know, mass opposes any kind of external force which tries to change the state of rest or of uniform motion. So mass is a measure of inertia in translatory motion. So in the translatory motion, if you want to push an object, you can see here, the man is just pushing a mass, so or pushing a body, and that body is opposing its external force. What is opposing? The mass of that object. Similarly, so we can say in translatory motion we have inertia and we need to apply external force to overcome that inertia. Similarly, in the case of rotational motion also, the body should possess rotational inertia or moment of inertia. So if you have to produce angular acceleration, you have to apply torque. Instead of force in rotational motion, we are applying torque, rotating effect of force. So if you apply a torque, you will produce or you will induce some angular acceleration in the object. Then the rotational inertia or moment of inertia will oppose your external torque. In short, we can say moment of inertia plays the same role of mass in translatory motion. So you please understand that concept. If somebody asking you what is this moment of inertia, it is the rotational analog of what? Mass. So in rotational motion, moment of inertia will oppose the external torque, or it is a rotational inertia of the object. In the second figure, you can see we have a mass m which is capable of rotating about a fixed point at a radius r. So mass is same. So you please understand, mass is same. If you are moving an object from north to south or from east to west, mass is same. It's constant. But moment of inertia is not a constant. It may vary. How it may vary? Because if you are just rotating this mass along this circular radius, and if you are increasing the radius of that circular path, you have to apply more torque. Because the moment of inertia will increase. You please see, the mass is same, m is same. What we did is we just increase the radius of that circular path, the distance from the axis of rotation. During that time, moment of inertia changes. So moment of inertia will depend on mass of the particle as well as the distribution of mass from the axis of rotation. So this is very important. Mass is constant, but moment of inertia is not constant. It depends on mass as well as the distribution of mass or the distance of mass from the axis of rotation. So depending on different axes, the moment of inertia of the same body may vary. So you please understand that point. Moment of inertia is not a constant. It depends on mass and distance from the axis of rotation. We can consider a life example. If suppose you have a ring. Suppose you have a ring and also you have a disc. You know what's the difference between this ring and disc? In the ring, the mass is only concentrated at its rim. Bangle is an example for a ring. But in the disc, the mass is uniformly distributed over the surface. Now you please say which one will have more moment of inertia. In the case of the ring, you know the mass is distributed at a particular distance. So the moment of inertia of the ring is more when it is compared with disc of the same mass. The mass is same, but the moment of inertia is different. This is because in the case of the ring, the mass is distributed at a distance from the center of axis. So this is what I like to mention, mass and moment of inertia. So moment of inertia is nothing but it is the rotational analog of inertia, rotational analog of mass. So now we need to find out how to find the moment of inertia of a particle. So moment of inertia, so this is the definition of moment of inertia. Moment of inertia of a particle is a product of mass of the particle and the square of the distance from the axis of rotation. Moment of inertia of a particle about the axis of rotation. So this is very important, moment of inertia of a particle about an axis of rotation, because I had told you already, moment of inertia depends on the position and direction of the axis of rotation. So moment of inertia of a particle about the axis of rotation is not a constant. If the axis of rotation varies, moment of inertia also varies. So moment of inertia of a particle about the axis of rotation is the product of mass of the particle and square of the distance of the particle from the axis of rotation. Here you can see, so this is the axis of rotation and the mass is at a distance of r from the point. So moment of inertia I equal to product of mass m into r square, and the unit is, you know, in SI unit of moment of inertia is kilogram meter square, and the dimensional formula is ml square. So this is the definition of moment of inertia of a particle. The next we need to learn the moment of inertia of a rigid body. I told you rigid body consists of a large number of particles. In the previous session we learned how to find the moment of inertia of a point mass or a particle of mass m, but here, you know, this is a rigid body, it consists of a large number of particles. How to find the moment of inertia of a rigid body? Imagine the body is made up of a large number of particles. I am just considering 3 particles, m1, m2 and m3, and these particles are at various distance from the axis of rotation. Suppose m1 is at a distance of r1, m2 is at a distance of r2 from the axis of rotation, m3 is at a distance of r3 from the axis of rotation. So in the case of rigid body consisting of a large number of particles, so the moment of inertia of the rigid body can be calculated by finding out the moment of inertia of the individual particles. So in this case we are just considering 3 particles, you know, m1 at a distance of r1, m2 at a distance of r2, m3 at a distance of r3. So, the moment of inertia of m1 mass at a distance of r1, you know, it is m1 r1 square. Moment of inertia of m2 at a distance of r2, it is m2 r2 square, and for m3 it is m3 r3 square. The body consists of only 3 particles. The total moment of inertia is given by I equal to m1 r1 square plus m2 r2 square plus m3 r3 square. So, if it consists of n number of particles, it is given by m1 r1 square plus m2 r2 square plus m3 r3 square plus etc. mn rn square, or it is simply sigma m r square. So, this is the moment of inertia of the rigid body. So, moment of inertia of the rigid body, about the axis is defined as the sum of the products of masses, the sum of products of the masses of different particles of the body and the square of their respective distances from the axis of rotation. So, it is given by these products of, or the sum of, you know, this is a summation sign, sum of the products of the masses of different particles and the square of their respective distances from the axis of rotation. So, this is how we are just calculating the moment of inertia of a rigid body. But think whether you are thinking that this is simple. Can you find out the respective distance of the particles in a rigid body and then you can use the same formula to find out the moment of inertia of the rigid body? No, it is very hard. It is very hard to find that the answer on that particular equation. So, we have another choice. Here we are introducing the term radius of gyration. Suppose we know if there are n number of particles, it is given by I equal to m1 r1 square plus m2 r2 square plus etc. plus mn rn square. The body consists of n number of particles. So, here we are assuming that the particles are having the same mass. So, it is m r1 square. So, we can write I equal to m r1 square plus m r2 square plus etc. plus m rn square. The particles are having the same mass. Take m outside. So, it becomes m into r1 square plus r2 square plus etc. plus rn square. Multiply n and divide it with n. So, it is m n into, because we have n number of particles. So, m n into r1 square plus r2 square plus etc. plus rn square divided by n. Okay. So, it is m n into r1 square plus r2 square plus etc. plus rn square by n. So, what is this m n? M is the mass of each particle, n is the total number. So, m n will give you the total mass of the rigid body, capital M. So, capital M into what? r1 square plus r2 square plus etc. plus rn square divided by n. So, mass into some term. I am just substituting that term as m, this one as k square. What is k square? It is r1 square plus r2 square plus etc. plus rn square by n. It is given as k square. What is this one? It is the arithmetic mean of the squares of the distance of the particle from the axis of rotation. So, what is k? K is given by k equal to, what is k? K is given by root of r1 square plus r2 square plus etc. plus rn square divided by n. So, k is the radius of gyration and it is given by square root of r 1 square plus r 2 square plus etcetera plus r n square by n, which is nothing but it is the square root of the arithmetic mean of the squares of the distance of the particle from the axis of rotation. So, it is nothing but the RMS value of the distance of particle from the axis of rotation. So, the point is very important, the radius of gyration. Radius of gyration is nothing but the RMS value square root mean square value of the distance of the particle from the axis of rotation. So, you can define radius of gyration in two ways. Either this is equal to the root mean square distance of the particle from the axis of rotation and the value depends on mass, the position and the direction of the axis of rotation. Or you can say you got the moment of inertia of the rigid body as m k square. In the previous case you got m1 r1 square plus m2 r2 square plus m n rn square, but here you arrived at the equation, it is m k square. So, the radius of gyration is that distance, the square of which when multiplied with the total mass of the body will give you the moment of inertia of the rigid body. You just multiply the total mass of the rigid body with a distance and that distance is called radius of gyration. So, you can define radius of gyration in these two fashion. First one, it is the RMS value of the RMS value of the distance of the particle from the axis of rotation, or it is that distance the square of which when multiplied with the total mass of the body will give you the moment of inertia of the rigid body. So, with this I am just concluding this part. Hope you understood. So, see you in our next session. Bye.